Okay, so let's chit chat about net forces because it's going to be one of the labs, the basis of the lab that we're going to start today and we'll finish up tomorrow. So if I had to make like a list of like most important things that you really need to understand out of physics, net forces would be at the top of the list, okay? So there's a couple of ways you can view this. But the idea being is that if you apply a force, you have to ask yourself, is there something working against that force, okay? And generally, the two forces you're going to have to worry about that can potentially go against that are either the frictional mafia or the gravitational mafia, okay? Those are the two that we're going to worry about the most. So if something's being lifted up in the air, so like if I want to take this cart and lift it up, if I don't apply enough force, upward force, I'm not going to lift it because the gravity mafia is holding it down too much. So if I'm going to lift this cart up, whatever force I apply has to be enough to overcome that frictional mafia. If I put this thing upside down and I try and push it, okay, if I apply just a little bit of force, I don't get an acceleration because I haven't paid off the gravity, the frictional mafia yet, okay? So one of the key things that you have to understand is that just because you apply a force doesn't mean that you're going to get an acceleration. So if I've got, you know, Hank the bowling ball here, right, and I apply some upward force, okay, my finger's straining pretty good, Hank's not moving. So, because I haven't applied enough upward force to overcome the downward force. Now, in contrast to that, if I take this cart and I put a wheel size down where there's just a tiny, tiny, tiny bit of friction, then I apply any kind of force at all, I get an acceleration. So, what's one of the key things that you have to ask yourself, okay, hey, what's going on in terms of an opposing force? So, if you look like on number 1, okay, with the semi. So in number 1, here's the setup, okay? So here's this truck, right? Right, we're going down the road, okay? And one of the first things you need to figure out is what forces are acting on the system and in which direction they're acting. So the truck's going this way, right? You hit the brakes, right? You hit the brakes. So what are the forces that are acting on this truck? There's 3 of them. What's one of them? Riley.
Gravitational force.
Okay, gravity's trying to pull it down, right? And I can find that by taking the mass times my gravitational acceleration, which is, Ellie, what's my gravitational acceleration? Beautiful, 9.8 meters per second squared. So I can always get that number, okay? It's going to be a big number, it's a big truck, right? Okay? Gravity's pulling down on this thing a lot. So, AHA, who was AHA? Okay, AHA, what's another force?
Force friction.
Now, if the truck's going this way, which direction is friction going to act? Opposite, okay? So we have an aha moment where we have the frictional forces going back this way. So, Suha, what's the third force?
The force applied.
No. And here's why, okay? So your applied force would be if you were still like pressing down on the gas pedal and giving it a forward force from the engine at the same time that you're hitting the brakes, okay? So this frictional force is what's going to make it stop, okay? We've removed the applied force because we're trying to make the truck stop, okay? So there is no applied force, okay? That's gone. Now, if I stop and then then I want the truck to speed up, then I have an applied force, okay? But this is just friction making it stop. So what's the third force?
Force normal.
Force normal, right? So I've got this acting up this way, okay? So here's what I've got. I've got gravity trying to pull this thing down. I've got my normal force provided by the road, and I've got friction going back this way. That's it. Now, here's what you're tempted to do. You're going, Oh, but the truck is going in that direction. There's a force making it go in that direction, okay? That's just inertia. Inertia is the tendency of that truck to want to maintain a constant velocity. So as soon as you hit the brakes, there is no applied force going forward, okay? It's not there. The only thing you have is this opposing force of friction going in the opposite direction. Now, at this point, when if I were to add all these forces together, I would not get zero. As soon as I know these forces don't add up to equal to zero, what do I know is going to happen? What'd you say?
It's going to accelerate.
It's going to accelerate. So I have imbalance forces, I have a net force, this thing is going to begin to accelerate. So when in doubt, and this is what I tried to convey in the video, make a chart that says FAP, FOP, FNET. So as soon as I know this thing is going to accelerate, I know this is not zero, okay? I know this is not going to be a zero value if this thing is going to accelerate. So I've looked at I drew a picture, I know which forces are acting on this thing. I have no applied force, so this is zero, okay? There's nothing there, there's no applied force. This is just zero. I'm going to have some opposing force, which is going to be my frictional force. And then if this is zero, so whatever force this is whatever my net force is. Okay? So the only thing going right at this point is the frictional mafia. I don't have anything trying to move it forward. I only have the frictional mafia. But the problem is, I don't know what that is. Okay? But here's what I do know. I have enough information to calculate the acceleration of the truck. Because I know the initial velocity, I know a final velocity, and I know how far it's going to travel when it stops. Okay? Now, this one you kind of work backwards. And here's one of the most important things you have to understand, is that it is only net force, and only net force, that equals mass times acceleration. Force applied doesn't equal mass times acceleration. Force opposing doesn't equal mass times acceleration. It's only the net force that equals mass times acceleration. Now, if your net force is your opposing force, then it's the same thing. But at the end of the day, it's only your net force that equals mass times acceleration. So what I have to do is I have to find that acceleration. So if you use that equation, you should get an acceleration something around -8 meters per second squared. Okay? So in number one, your acceleration should be around -8. Okay? That's an ish, but it's somewhere around in there. Okay? So then I can take that mass of 2.73 e to the fourth kilograms times -8 meters per second squared. Okay? And again, don't use -8. Your answer is somewhere around -8. Okay? Don't use -8. This is just an estimate. But here's the point, is that once I get this number, then I know my net force, then I know my frictional force. So these two numbers are going to be the same because there is no applied force working on the system. So this is what's going to make this thing stop. So your answer to number one should be a negative number and something times 10 to the fifth. Okay? It's going to be a pretty big number. Now, when you get to number two, you want to calculate the coefficient of friction. Well, mu is going to be force friction over force normal. So what you just found up there is the frictional force. Okay, that's the number. Okay, that is the frictional force. You have that because that's what's making it stop. Then you're going to divide that by your normal force, which is going to be mass times my gravitational acceleration. So you can take that mass, multiply that by 9.8 meters per second squared. Boom, there's that number. So your answer to number two should be around 0.8. Okay? And again, remember with the coefficient of friction, there's three things you need to remember about mu. It's never negative because it's an absolute value. It has no units because it's a ratio of forces. And it's rarely above 1. Okay? Rarely is it above 1. Most of the time it's, 0.1 to 0.8. Even that coefficient of friction, 0.8, is kind of a high value. Speaking of coefficient of friction, there's a slight chance of snow Sunday night, so if you all are driving to school on Monday morning and it has snowed, remember ice and snow have a very low coefficient of friction, which means you're stopping, your velocity time graphs are going to be very shallow when you try to stop. Leave lots of room between you and the people in front of you if you're driving and it has snowed or there's ice, okay? Because it's like a low mu day, leave lots of gaps between you and the people around you. Okay, now on number 3, what are the 2 most important words on problem number 3? Beautiful, constant velocity. Those are the 2 most important words on problem number 3. So in problem number 3, again, set this up and go, hey, here's this chair, right? And we've got the mass. So right away I can figure out how much it weighs and I can get my normal force. So again, I've got my gravitational force acting down. I've got my normal force going up, right? Now, Reha, because I'm at a constant velocity, what do you know about the applied force and the frictional force?
They're the same, just opposite sign.
Beautiful answer, okay? So I've got this force applied going this way, and I've got this force friction going in the opposite direction, okay? So if I can find one of those, I automatically know what the other one is, okay? As soon as I know one, I know what the other one is. So you're given that it takes 16.4 newtons of force to pull it, so that's my applied force. So right away I know what my frictional force is. Okay, I hooked up a scale, I pulled it, right? So on that one, that mu on number 3 should be somewhere between 0.2 and 0.3. Okay, it's a pretty small number. Now, on number 4, number 4 is the easiest problem on the entire assignment. Okay? It is the easiest problem on the entire assignment. All you've got is that here's a box, and I'm going to apply a force of 18 newtons to it, and I'm going to make it accelerate. I haven't given you anything about force friction, gravity. We're not lifting it up in the air. We're not doing anything weird. Okay? It's just like, here's this box. It's on a perfectly frictionless surface. I'm going to apply a force of 18 newtons to it. I want to know what the acceleration is. So when in doubt, draw this chart. I cannot emphasize this enough. Go, okay, force applied, force opposing, force net. So you're told that you're applying a force of 18 newtons. I didn't give you any information about friction. I didn't give you the coefficient of friction. You're not lifting the box up in the air. There's nothing to do here. This is just 0. So all of that force goes to accelerate the box. Now, this wouldn't happen, but stay with the story, okay? So let's say that Ellie's down in the lunchroom, and there's this freshman who doesn't have any money, okay? And freshman's hungry, and so Ellie takes pity on the freshman's little soul and says, hey, you have a nice watch, okay? Why don't you just give me the watch? Okay. And so Ellie takes the watch from the freshman. Okay, she wouldn't do this, but let's just say, okay? Now the kid is going hungry and the kid doesn't have any money. Or doesn't have the watch because Ellie took the watch. Okay? Like I said, this is not going to happen. It's a story. Okay? Now, so she's got the watch. Okay? Aha sees the watch and says, wow, hey, I need a watch. Ellie says, I'll sell it to you for 18 bucks. Girl, Aha goes, I like that idea. Okay? So, Aha pays Ellie 18 bucks. Now, what's Ellie's net profit on the deal? 18 bucks, because it didn't cost you anything to get the watch, right? So you're going to make $18. So that's what's happening here. You're applying 18 newtons, but you have nothing against it. Okay? So you get to keep all $18, and the freshman goes hungry. I hope you feel that. Okay.
I stole his watch and didn't pay for his lunch.
Huh?
I stole the watch and didn't pay for the lunch.
Well, we'll get to that.
Okay.
Now, on number 5, now we're going to have Ellie pay for the lunch. Okay? So what's happening on number 5, I've given you the coefficient of friction. So on number 5, I've given you that mu is 0.540. So now what we're going to do is figure out how much Ellie is going to give the freshman for lunch. Okay? That's what mu is going to allow us to calculate. We're going to calculate how much she's going to pay to the frictional mafia. So you're going to go mu times force normal equals force friction. So when I do this, when I take that 5.540 times the mass times 9.8 meters per second squared to be that force normal, that's my frictional force. This is how much Ellie is going to give the freshman. So if you do that right, that frictional force is around -8. Okay, pretty close to -8. So that's going to be something pretty close to -8 newtons. So here's what this means. Ellie, out of the kindness of her heart, is going to say, hey, I'll take your watch, okay, but I'm going to give you $8 so you can have lunch, okay? So she has given $8 to the freshman, but she still has the watch. She walks in, the watch is sitting on the moment, or on the chair, the AHA walks up and says, wow, that's a nice watch. I'll pay you $18 for the watch. Now, Ellie gave $8 to the freshman. AHA gives her $18. What's Ellie's net profit? $10. Okay? So that's what's happening once you introduce friction. So on number 5, if you set up that chart, which I highly recommend, so there's still an applied force of 18 newtons. We have an opposing force of about -8 newtons. So my net force then is going to be about 10 newtons. Okay? This is round numbers, but this is actually pretty close. It's pretty close to about 10 newtons. Now to get the acceleration, I want to take the 10 newtons and divide that by the mass to get that acceleration. So here's what I want you to think through. Your answer to number 4, okay, that acceleration is 12 meters per second squared. Okay, there's your answer to number 4, 12 meters per second squared. Do not miss number 4, there's the answer. Show me your work, but there's your answer. So here's the deal. If an 18 Newton force without friction creates an acceleration of 12 meters per second squared, okay? Soha, okay? No. Was it Soha? Yeah, Suha, Reha, Aha, and Soha. Okay. We got to get that straight. The Ha sisters. Okay. So, if there's friction, okay? So, if there's no friction, like this, I apply that force, I get an acceleration of 12 meters per second squared. Now, if there is friction, what's going to happen to my acceleration? Is it going to be more or less than 12 meters per second squared? Less. Because now the frictional mafia is going to be taking away some of that. Okay? Ellie had to give the freshman some money. Okay? So it's going to be working against that. So your answer to number 7 has to be less than 12 meters per second squared because of the fact that you have paid off the frictional mafia. So your answer to number 7 should be around 7. Okay, that's an ish, but it should be around 7. Okay? Now, what I want on a drawing from number 5, okay, pay attention to exactly what I want on number 5. You're going to have 2 sets of diagrams, and this is drawn to scale with a ruler. Okay, this isn't a sketch. Okay, that's why I said I want this as with a suitable scale. This isn't a sketch. So what I'm looking for is 2 diagrams. One where you're going to have your force normal as a free body diagram, your gravitational force, your force normal, that force applied, and that force friction. So this is like 18, this is that -10, here's my normal force, here's my gravitational force. And you have to draw these 2 scale. You have to multiply that mass by 9.8 meters per second squared and get these numbers. Okay? And if you want to let 1 centimeter equal Newton, that's fine. If you want to let a ½ centimeter equal Newton so you don't have this big mass, I don't care. But you have to show me what the scale is. You can't just randomly draw lines and go, oh, this is what the force is. Okay, these have to be drawn to a specific scale. So that's what one of them is going to look like. What the other one is going to look like is when you draw that tip to tail, I always draw my gravitational force first. And there's my applied force. There's my normal force. There's my force friction. Now, make sure that you draw the resultant, okay? That's the whole point of this. You don't end up back at the origin. That's what makes this system accelerate, is the fact that you don't end up back at the origin. So make sure that this is where you go back to, this is why we learn how to draw vectors first. Root, you always draw that resultant from the origin out to wherever you end up. So make sure that you draw and fill in this gap and say, oh, here's my net force. So what this line is going to represent is the net profit that Ellie gets to keep out of the deal. So if there was no force friction, this would go all the way back to here, and she would make $18. But because of the fact that she's got to pay off the freshman, so the freshman can have lunch, or pay off the frictional mafia, however you want to think about it, that's going to take away from some of this, and that's going to decrease that net force. We're good. Good? Okay. All right. Now, let's talk about number 8. So, the first 7 problems dealt with paying off the frictional mafia. Okay? So, in number 8, we're going to deal with the gravitational mafia. So, on number 8, here's the setup. So, here's your rocket. Okay? And you have an upward force of 129 newtons, and you want to find, ultimately, the acceleration. And you know the mass of this rocket is 5 kilograms. Now, here's what you're tempted to do. And I promise you, you mark my words. I'm going to give you a problem like this on the test. I'm going to say, here's the upward force out on this rocket. What's the acceleration of the rocket? And here's what you're going to be tempted to do. Oh, F equals ma, right? I'm going to take 129 newtons, I'm going to divide that by 5 kilograms, and I'm going to say, oh, there's my acceleration. Physics isn't so tough. Look, I are smart. I did rocket science, okay? I found the acceleration of the rocket. I took 129 and divided it by 5. I are smart. 10 out of 10 for me. And I'm going to go, no, stop, it's wrong. Why can you not just take 129 newtons and divide it by 5 kilograms? What's missing? What do you not take into account? Who did you not pay off?
Gravity.
Yes, you have not paid off the gravity mafia, and they are going to hunt you down. Okay? So again, set up a chart, go FAP, force opposing, net. So the 129 newtons is what's trying to get this rocket up in the air, right? So, what's going to be working against you when you try and launch this rocket up in the air? Who are you going to have to pay off? Gravity mafia. So, you're going to take 5 kilograms times 9.8 meters per second squared. You get like negative 49 newtons. So, you've got an opposing force of 49 newtons. That's how much money you have to pay to the gravity mafia. Whatever's left over is what your net force is going to be. Okay? So, that answer on 8B should be 80 newtons. Because if that's wrong, everything else you do on this problem is going to be a train wreck. Okay? So your answer to 8B should be 80 newtons. Ellie paid off $49 to the freshman. She sells it, it's a really, really nice watch, okay? So she sells it for 129 bucks. She keeps 80 bucks out of the deal, okay? So that's what's left over to actually accelerate the rocket. So your answer to D should be around 200 meters per second, okay? And some of you are beginning to really, really, be terrible at significant digits. Every number that I gave you on number 5 has a minimum of 3 significant digits, okay? So all of your answers should have 3 significant digits, okay? Just saying. Now, what I want on the free body diagram is something simple. All you want to do is show the forces, the velocities, and the accelerations. So when this rocket takes off, just go, oh, here's my applied force. Here's my gravitational force, right? If you want to, you could draw in your net force pointing up. So when this rocket takes off, okay, first off, which direction are your velocity vectors going to point? Up, down, or sideways? Hopefully up. Okay, if they don't, Houston, we have a problem. Okay? So just go V1, boom, V2. So my velocity vectors are getting bigger, pointing up. So what's the direction of my acceleration vectors? Pointing up. And the reason that my acceleration vectors point up is because my net force points up, because I have more applied force than I have opposing force. So hopefully that all then makes sense. Now, when you get to the backside, you're traveling at about 200 meters per second, about 2/3 the speed of sound. Okay? So at that point, we shut off the engines. So that's like me taking this ball and throwing up in the air at 200 meters per second. So go to this chart. I shut off the engines. What do I lose? What's missing? Yeah, this goes to zero. Okay, there is no applied force acting on the system. What's the only force I have left? Gravity. That's my net force. Guess what the acceleration is going to be? Negative 9.8 meters per second squared. Okay? So, as soon as you shut off the engines, that's like throwing that golf ball up in the air. As soon as it leaves my hand, this goes to zero. I still have gravity. That's my net force. My acceleration is going to be negative 9.8 meters per second squared. Now, on that velocity time graph on the back side, make sure that you label everything that I want on that. Okay, there's a whole bunch of things that you need to put on there, and and that graph is going to look something like this. Okay, when you get done, that's what that thing's going to look like. And if you do this, and like let's say that you have to add on to the time, like you need more than 36 seconds, no, something's wrong. Okay, if you have a velocity of like 400 meters per second, you're going, wow, Burkamp screwed up. He didn't make the scale big enough. I need a velocity of no. Okay? You've done something wrong if your velocity and time will not fit in the parameters of the scale that I gave you. Okay? Just saying. Don't go, well, Burkamp's an idiot. He screwed up. No. Okay? So make sure on E, and you can either do it on the sheet or you can do it on another sheet of paper. I want to see two distinct sets of drawings. Okay? I want to see what's happening on the way up, and again, this is after you've shut off the engines. So what's happening as that rocket is approaching its maximum height, and then what's going to happen when that rocket starts to fall back down. Okay? So I want label it. Oh, here's what's going up, here's when it's going down. Okay? Are we good? Okay. Now, here's a common misconception that I've seen kids try to do. And that's on number 9. It said, wouldn't be the acceleration of the same rocket was launched straight up, but there was no gravity. Okay? You still have the 129 newtons as your applied force. I've seen kids try to subtract out the 5 kilograms and go, oh, my net force is now 124. So first off, you can't subtract kilograms from newtons. No matter how much you try, you can't do this. Because they're going, well, but it has mass. So it does. And so where we take that idea into account is when we take that 129 newtons and we divide it by the 5 kilograms. So when you divide by the mass, that's how you account for that idea that, oh, there's an opposing force. That's why you divide by the mass. So that's where that's taken into account. So on that last one, on number 9, don't subtract out 5 kilograms because you can't even do that. All you have to do is take 129 and divide it by 5 kilograms. There's your acceleration. That's all you have to do. Don't make it difficult. okay? And you should see that that acceleration is a lot bigger than the first one, because now you're not having to pay off the gravity mafia. So when you're launching a rocket, unless I specifically tell you that the effects of gravity can be ignored, you take gravity into account, okay? And I literally, there will be problems, I will tell you, like this one. Don't worry about gravity. But unless I specifically tell you not to worry about gravity, you worry about gravity, okay? Now, when you answer, and I'm just going to point this out because some of you, I don't think, know how to answer questions. So on number 10, I said, why are they very concerned about keeping rockets designed to minimize mass? And I say, explain in terms of opposing forces, net forces, and acceleration. What three words do you, or three concepts do you think you should have on that answer on number 10?
Opposing net and acceleration.
Yeah. If you read your answer and you haven't used the words opposing force, net force, and acceleration, guess what? You've missed the whole point of the question. When I specifically say, here are the things that I want addressed, guess what? Those are things you probably talk about when you answer the question. I know that's a radical concept, but I'm just always appalled. And here's the other thing, and I've seen this happen in the, maybe the past 3 or 4 years. Like when you answer the question, like when you guys give your answer, like you restate the question, okay? Like, oh, they're worrying about this because, look, I wrote the question. I know what the question is. Don't tell me the question again, okay? Just answer the question, okay? Don't waste your time and don't waste my time and restating the question. I know what it is. I wrote it. Just answer the question, okay? And it's weird. That phenomenon just started like 3 or 4 years ago. Okay? It's just weird. I don't know. Someone somewhere down the line said, oh, we're going to teach you. No, stop. Don't.
It's been burned into our heads.
Huh?
It's been burned into our heads.
Unburn it. Okay? Unburn it. Stop. Okay? Don't. Anyway. Okay. Well, it's just frustrating. It's like, I only have so many hours left on this earth. I don't want to waste it rereading a question that I wrote. Okay? I get it. You can read. We're happy for you. Answer the question. Okay. I'm just saying. Do you see my point? I mean, if you were me, it's like, great. I have to reread the same question 13 times because you all think it's cool. No, don't. Okay. Anything else you want me to go over on that net forces? Hopefully that all makes sense. We're good? Okay. So, we've got some videos to watch on launching the space shuttle. So, a little bit of history on the space shuttle. That used to be the means that the United States had to launch satellites, get people to the International Space Station. But the technology got old and they retired that. And now, like, Elon Musk and his company are trying to take that place. So the footages of the space shuttle, we don't use them anymore, but it's the same idea. So basically, when you look at launching rockets, there's two potential types of rockets you can use. What's called a solid rocket fuel, and which is great because it's simple. These are like the big dumb rocket engines, but it's a solid fuel. There's no pumps. It's simple. You light it, and then it burns. So it's kind of like a firecracker. But the problem is that once you light it, you can't shut it off because there's nothing to shut off. It just has to burn itself out. So the solid rocket boosters are cool, but you can't shut them off. So then you have the typical rocket engines, and those have these complex pumps and valves and all this stuff. And those are cool and they work really well, but the advantage is that you can shut them off if you need to. So that's kind of the balancing act. So basically it's cool because it goes through and talks about like the physics of this in terms of how it works and net forces and all that. So now when you watch this, now you should be able to look at this and go, okay, yeah, now I know what we're talking about on this deal. So one of the equations they're going to talk about in here is that you all are used to seeing force equaling mass times acceleration. And if you rewrite this a little bit, acceleration is v minus v naught over time. So basically, you're talking about acceleration as being a change in velocity over time, and you keep the mass constant. Okay, that's how you all are used to seeing this equation. When you talk about rocket engines, though, you change this a little bit. So that's change in mass over time multiplied by velocity. So when you talk about rocket engines, and they'll talk about this in this video. This is and we'll use this once we get into momentum. This is the velocity of the gas that's being ejected out of the bottom of the rocket engine. This is change in mass per unit of time. So all I did was I took the time, instead of putting it underneath the velocity, I put it under here. So this is how much mass this rocket engine consumes and can run through the engines. So if you want a lot of force, you want those rocket engines to escape or push gas out at a very high velocity, and you want it to consume a lot of mass per unit of time, okay? That's how you generate a lot of force. But so it kind of becomes a catch-22. You say, okay, I want to generate a lot of force. Oh, I'll build a really, really big rocket engine that can consume a lot of fuel per unit of time. But so this is where it becomes like a battle. Well, it's like, well, we'll build big rocket engines. Okay, cool. Guess what? Big rocket engines weigh a lot. So then, by building this big rocket engine, now you've added to the weight of the rocket that you're trying to get up in the air. So unless increasing the size of the rocket engine gives you an appreciable increase in force, you're actually losing ground by building bigger rocket engines because they weigh more. So that's kind of the battle. It's like, okay, we'll build big rocket engines. Big rocket engines weigh more. They have more mass. They have more inertia. It's harder to get them up in the air because the gravity mafia goes, wow, we really like big rocket engines. They're cute. They're cool. We're going to charge you a lot of money to get that puppy off the ground. So it kind of becomes an arms race. Okay, so I got to switch over some stuff. If you want to stand up, take a stretch. I got to like switch cables and do all sorts of weird stuff here. Okay, we have video.
Ignition.
Okay.
Liftoff.
Over the past few decades, accomplishments in spaceflight have proven to be some of man's most triumphant achievements. The underlying principles which made these achievements possible came as a result of hundreds of years of investigation into the behavior and structure of matter. It's these principles of physics which play the foundational role in making spaceflight a reality. Launching of a rocket provides a spectacular display of force and energy. From a physics viewpoint, a rocket launch vehicle can be thought of as a large force machine. Its sole purpose is to apply a continual thrusting force in order to produce an acceleration. If the rocket is to achieve a low Earth orbit, the magnitude of the acceleration which is required tends to be quite large. The rocket must go from a state of being at rest on the Earth's surface to that of traveling 8,000 meters per second at some given distance.
That's about
above
5 miles per second.
This tremendous velocity change takes place over a relatively short period of time and necessitates the large amount of energy and acceleration provided by a rocket launch vehicle. The single most important component of a launch vehicle is the rocket engine.
That's actually the
Use of
size
a
of
rocket
5
engine
rockets
provides
that shot
the
us to
means
the
by
moon.
which thrust
So
is
that gives
produced
you
to the
some
maximum
scale as
space.
far as how big those engines
Since
are.
oxygen is not present in the space environment, an oxidizer must be carried on board the rocket along with the fuel. The Space Shuttle's propulsion system is made up of 5 different rocket engines, 3 main engines which use liquid propellant, and 2 rocket boosters which use a solid propellant. The tremendous temperature extremes which the Space Shuttle's liquid propellant main engines operate at required innovative engineering during their design. The engine's complex system of precision valves and pumps must handle the extremely cold propellants without freezing up. The liquid hydrogen fuel at minus 253 degrees Celsius is the second coldest liquid on Earth. However, when burned with liquid oxygen, the temperature in the engine's combustion chamber reaches 3,300 degrees Celsius, a temperature higher than the boiling point of iron.
Okay, so this is why this is so tough to build these, okay? So you have liquid hydrogen and you have liquid oxygen. Okay, so if you've ever seen, in a chemistry class, if you've ever seen like a hydrogen balloon explode, okay, that's basically what's happening here. So the reason that they go through this process of cooling it down to make it a liquid is because in the same amount of space, you can have a lot more fuel as a liquid than you can as a gas. So helium is actually the coldest liquid on Earth. So if you want to make, so here's a quick lesson in chemistry. So if you want to make something turn into, from a gas into a liquid, whether that's nitrogen, oxygen, whatever that is, you have to cool it down so that when these gas particles run into each other, they stick together. So it's kind of like second graders, okay? If it's a warm day, you have a room full of second graders and they're out on the playground and they're bouncing around, they're not going to stick to each other, okay? But if the cold front comes through and the high temperature is like 25 degrees and they're out there, those kids are going to tend to huddle together. And they're going to go from like these obnoxious little gaseous particles running around all over the place, and you're going to cool them down and they're going to begin to stick together and they're going to form a liquid. So that's what happens with hydrogen. Hydrogen is very difficult to get as a gas because it's not very sticky. Okay? Helium is even less sticky. Oxygen, nitrogen, the bigger molecules, those are more sticky, so it's easier to get them to turn into a liquid. And that's a whole discussion of something called van der Waals forces. Take AP chemistry, I'll give you the whole story with that. But, so, in contrast, you have, within this system, you have the second coldest liquid on Earth. Once that heats up and expands and creates this big fireball, not only is that temperature hot enough to like kind of warm up steel, make it glow red, that temperature is hot enough to make steel boil. Okay, so imagine, you all have seen boiling water. You all made macaroni and cheese. Okay, imagine that you have a pot full of boiling iron. So that's the challenge that exists. So you're going from having a really cold substance into something that will boil iron all in the same system. That's why it's so difficult to build these engines. Whoa. That wasn't supposed to happen.
In the combustion chamber of the rocket engine, the propellants are consumed in a combustion reaction. The thermal energy generated from the combustion heats the newly formed gases to extremely high temperatures. These gases, possessing a large quantity of kinetic energy, subsequently go through an expansion in the rocket nozzle and are ejected at extremely high velocities. With the fuel being composed of liquid hydrogen and liquid oxygen, the hot gas which is expelled from the engine is primarily water vapor. The thrust which is produced by the engine can be explained in terms of Newton's third law. As the engine applies a downward force on the gases, causing them to be ejected, the gases must also apply an equal and opposite force, pushing
So
upward
notice
on the
that,
engine.
and this is what I tried to
This
show
upward
you
force.
with the balloon on the string. This set of equal and opposite forces occurs within this system. It isn't the gases pushing here and then the gases pushing back up off of anything. That set of equal and opposite forces occurs within the engine. This is what allows us to operate in space, because if you had to have these gases pushing against something, you couldn't make ships work in space, because there's nothing to push against, because it's a vacuum. This is why you have to understand, this is where the set of equal and opposite forces play out.
Pushing on the rocket engine is essentially a reaction force to the gases being pushed downward, and is responsible for giving the engine its upward thrust. Newton's second law of motion, expressed in terms of momentum, can be used to find the magnitude of the thrust produced by a single space shuttle main engine. With the propellant gases being ejected at a velocity of 3,600 meters per second, and at a rate of 470 kilograms per second.
Okay, so 3,600 meters per second is about 10 times the speed of sound. Okay, speed of sound is about 330 meters per second. So these particles are being injected at 10 times the speed of sound. 470 kilograms, that's about 1,000 pounds. So this is about like a small car. So each engine per second is consuming the same mass as a small car, and it's kicking that gas out at 10 times the speed of sound. That's what's creating such force out of each one of those engines.
The resulting thrust generated by the engine is equal to 1.7 million newtons. As seen by the second law, the greater the rate at which the hot gases are exhausted, and the greater their velocity, the greater the resulting thrust will also be. Solid propellant engines make up a second group of rocket engines. These engines are much simpler in design due to the fact that they require no pumps, valves, or complex propellant feed systems. However, once ignited, they cannot be shut down.
That's
The shuttle's
downside.
solid rocket boosters use a propellant which consists of aluminum powder as the fuel and ammonium perchlorate as the oxidizer. A rubber-based polymer binder is also added. This mixture fills the entire length of the solid rocket motor, except for a hollow channel extending through its center, which serves as a combustion chamber. When ignited, the propellant burns from the center out towards the sides of the casing at a nearly constant rate. An extraordinary amount of thrust is created.
Yeah, don't stand
Propellant
behind
gases are
there.
exhausted at a velocity of 3,300 meters per second and at a rate of 4,000 kilograms per
So
second.
now you're up to 4,000
13
kilograms
million
per second.
newtons
So
of
that's
thrust.
like 8 cars
Enough
per
thrust to
second.
maintain the flight of 20 747 airliners. The Space Shuttle system is the most technologically advanced and complex machine on planet Earth. Unlike the Saturn V rocket, which carried its payload to the moon, the shuttle is designed to attain a low Earth orbit. Achieving the necessary orbital velocity is no small task, as it requires the combined thrust of the shuttle's 3 main engines and 2 solid rocket boosters. With the large external tank storing the liquid propellant used by the main engines, and the 2 solid rocket boosters containing their own solid propellant, the total mass of propellant aboard the shuttle equals an enormous 1.7 million kilograms. This propellant mass accounts for 85% of the shuttle's total
So
launch
basically, it's a
mass,
big flying
and
fuel
provides
tank.
20 billion kilojoules of chemical energy, which is necessary for attaining orbit. The filling of the liquid oxygen and liquid hydrogen tanks occurs on the launch pad several hours before launch. The oxygen vent arm, which caps the top of the external tank, allows vaporized oxygen to escape from the tank, and thus prevents the tank pressure from building up to excessive levels. A similar arm allows the lower positioned hydrogen tank to also be vented. As the final countdown begins, the flight crew is
The
taken
guy on the
over
right has to be a
and enters the
NASCAR
order by
fan.
way
Check
of
out those
access arm.
sideburns.
With all systems checking out and working order, the crew access arm is retracted at 7 minutes before launch. At 3 minutes before liftoff, the main engines are swiveled to their proper launch positions. All of the shuttle's engines are mounted on a pivot device, or gimbal, which allows the flow of exhaust gases and the direction of thrust to be controlled during ascent. The oxygen and hydrogen vent arms retract at just 2 minutes before engine ignition. At 7 seconds before launch, the sound suppression water system starts dumping 300,000 gallons of water onto the pad. This water is used to partially absorb the 170 decibels of acoustical energy given off by the engines, preventing it from fully reflecting off the pad and causing damage to the shuttle. Hydrogen igniters under the main engines are used to ensure that any hydrogen flowing out of the engines prior to ignition is burned off as it emerges. This prevents the buildup of a potentially hazardous cloud of explosive gas.
That would be bad.
At 6 seconds before liftoff, the 3 main engines are ignited. Shock waves coming out of the throats of the nozzles cause them to vibrate momentarily.
Okay, so at this point, here's what's happening. So here's one of the solid rocket boosters. Those haven't been started up yet. So you got these big 3 engines firing. So here's the question. So it's impressive, okay? It's loud. These things are firing. It's cool. But why isn't the space shuttle taking off? You're firing these 3 engines. Why hasn't it taken off?
Not giving enough force to.
To what?
To pay off the gravitational.
Yeah. At this point, the downward force is more than the upward force created by the rocket engines. So what that means is if you pull that launch pad out from underneath this thing at this point, the space shuttle would begin to accelerate downward. Now, not at 9.8 meters per second squared, because you do have some upward force, right? But at this point, the applied force isn't enough to overcome the gravitational force. You're not going anywhere. So that's like if I go to push on this cart, okay? If I apply a little bit of force and that's not enough to overcome the frictional mafia, that cart doesn't move. Same thing's happening here. I'm applying this upward force, but it's not enough to overcome the weight of the ship. So even though this is the classic example, yes, I'm applying a force, but I'm not getting an acceleration. Now, the other reason that you start these engines first, because if you start these 3 engines and say there's a problem with one of them, you can shut them down, okay? Because these run off of pumps. That's why you make sure these are working, and then you start the solid rocket boosters on the side. Because you don't want to start the solid rocket boosters first, and then go, oh, the battery's dead, one of the engines isn't going to start, this is bad. And then you got these solid rocket boosters going crazy, and then you can't, it's like, oh God, you're going to get the jumper cables. No, you're screwed at this point. So this is why you start these first, then you start the solid rocket boosters.
At T-minus 3 seconds, the main engines reach 90% thrust. 1/2 second before liftoff, the solid rocket boosters are ignited as explosive hold-down bolts are triggered. During the initial part of its ascent, the shuttle's engines deliver a combined power of over 100 billion joules per second, an amount of power which is equivalent to the output of 85 Hoover dams. A distinction can be made between the different types of engine propellant, as the main engines are observed to burn with a clean light blue flame as a result of the hydrogen and oxygen combustion. This contrasts with the solid rocket boosters, which burn with a bright orange flame due to the combustion of the solid aluminum fuel. The dynamics of the launch can be studied in more detail by examining the forces involved during the shuttle's ascent. With the 3 main engines ignited and applying their combined thrusting force of 5 million newtons, the shuttle still remains motionless. At this point, the upward thrusting force represents only a fraction of the total shuttle weight, which is equal to 20 million newtons. If the supportive launch
Now
pad
watch
is
off to
away
the
during
right
this
when they
period,
start the solid
the net
rocket.
force would cause the shuttle to accelerate downward. In order for the shuttle to accelerate upward, the total thrusting force must be greater than the shuttle's weight. This takes place when the solid rocket boosters ignite. With the 2 solid rocket boosters applying an additional 26 million newtons of thrust, the total thrust from all engines is now 31 million newtons. At this point, the net force is directed upward and the shuttle lifts off. The initial upward acceleration can be determined by using Newton's second law of motion. With a net force of 11 million newtons acting on the total shuttle.
Okay. So this is the most important thing that you have to understand. Okay. So this is what you have available. 3.1 times 10 to the 7th newtons of upward force. This is what the ship weighs. This is what you have to pay off to the gravity mafia. The difference between these two is what you have left over. This is this net force, okay? You divide that by the mass, boom, you're going to get your acceleration. Now, Hannah, think this through. As this thing takes off, okay, what's going to happen to the mass of the space shuttle? What'd you say?
I think it's gonna stay the same.
No. You're burning fuel. You're taking all of that fuel that was in there and you're kicking it out through the engines.
It's gonna get smaller.
It's going to get smaller, okay? So, here's the deal. If this number stays the same, because that's the force generated by the rocket engines, okay? So if this number stays the same, it's going to weigh less. Because what Hannah just said is that it's going to weigh less because of the fact that this thing is going through the fuel. So if I have the same applied force, and I decrease the weight, then Hannah, what's going to happen to my net force?
And then it's gonna get smaller.
It's going to get what?
Smaller?
No. Think about this. This number's staying the same. I'm giving less money to the gravity mafia. So what's going to happen to the amount of money I get to keep?
And get more.
It's going to get more. So here's what's happening. As it flies up in the air, my net force is actually getting bigger. Okay? Now, here's the other cool thing about this. The mass that I have to accelerate is actually becoming smaller. So what happens is, over a period of time, is that we haven't talked about this, but if you were to look at like an acceleration time graph, your acceleration actually is going to get bigger as time goes by because you have two things working. You're having a larger net force, so this is continuously getting bigger because you're decreasing the weight of the ship. And you're continuously dividing by a smaller and smaller mass, so that's going to make the acceleration get bigger and bigger and bigger. So when this thing takes off, you all are used to having acceleration remain constant. In this case, the acceleration actually becomes bigger. So you're accelerating your acceleration, if that makes sense. Okay.
Mass of 2 million kilograms, the initial acceleration is equal to 5.5 meters per second squared. With the thrust initially remaining constant, the shuttle's acceleration will continually increase as the engines expel their propellant and reduce the mass and weight of the shuttle system. With 9,400 kilograms of propellant being exhausted every second, the shuttle's mass becomes reduced very quickly. After only 30 seconds into the flight, the shuttle is traveling with an instantaneous velocity of 200 meters per second. At this point, the engines have already expelled 280,000 kilograms of propellant, reducing the shuttle's total mass and weight by 14%. Newton's second law of motion shows that the acceleration has now increased to 8.2 meters per second squared. At approximately 50 seconds into the flight, the shuttle enters a critical period during its ascent as its velocity approaches the speed of sound. As the shuttle moves through the atmosphere, it creates a disturbance in the surrounding air. The resulting pressure waves spread out in spherical shells at the speed of sound. As the shuttle approaches the speed of sound, it begins to catch up to the pressure waves it produces. With the distance between wave crests becoming successively smaller, the waves begin to pile up in front of the vehicle, creating a wall of high pressure. This pressure barrier, sometimes referred to as the sound barrier, presents resistance to the
Because
shuttle's
for a
motion.
long time, we thought
Breaking
that
through this
planes
pressure
couldn't
barrier
fly
creates a
fast
period
with
of
speed of
maximum
sound because
dynamic
that was,
pressure
we thought it was like
and
an
results in a
invisible barrier that
considerable
the
amount of
planes couldn't get
aerodynamic
through.
stress being imposed on the shuttle. To minimize this stress, the shuttle throttles down in an effort to reduce its acceleration at the time of passage through the pressure barrier. After breaking through the barrier, the pressure becomes greatly reduced, and the shuttle's motion is no longer impeded. With the shuttle no longer experiencing the high level of aerodynamic stress, its engines are throttled back up to 100%. Now, traveling faster than the speed of sound, the shuttle outruns the sound waves it produces. The resulting pattern of waves leads to constructive interference taking place, where successive wave fronts overlap, forming a single very large wave front, which carries a tremendous amount of sound energy along with it. This large wave is called a shock wave and forms a conical shell of sharply increased pressure with the shuttle at its apex. Throughout the remaining atmospheric portion of its ascent, the shock wave will continue to trail behind the shuttle. After 100 seconds into the launch, the engines have expelled an enormous 940,000 kilograms of propellant, reducing the shuttle's total mass to almost half of what it was at the time of launch. With this decrease in mass and resulting increase in net force, the shuttle's acceleration has climbed to 18 meters per second squared.
So what that means is if you're in the
During
space
this
shuttle,
period of
it's going to
time,
feel twice
frictional
as
heat
heavy as you
caused by
do
the
right now.
atmosphere reaches its
You all are
maximum
used to
level,
living under
as
1
collisions with
G,
air molecules
that's like 2
cause
G,
portions
so
of the
your
shuttle's
arms would
exterior
feel twice as
to reach
heavy as you do
temperatures of
right now.
1,000 degrees Celsius for a short time. At 2 minutes into the flight and at an altitude of 45 kilometers, the two solid rocket boosters have consumed nearly all their fuel and no longer provide thrust to the shuttle. At this point, the shuttle's weight can be considerably reduced by dropping the spent booster casings. The boosters are released by explosive bolts and are then powered outward and away from the shuttle by 4 small separation motors on each end of the solid rocket boosters.
Okay.
The reusable booster casings perish.
So what you're going to do in the lab, which we're going to start today and finish up tomorrow, is going to be dealing with trying to land a spaceship on the moon.
Sending a manned spacecraft to another planetary body presents an enormous scientific challenge. That challenge is immeasurably escalated by having to also return the manned spacecraft safely to Earth. The extremely successful Apollo missions made a total of 6 different manned landings on the surface of the moon. The lunar module, consisting of a lower descent stage and an upper ascent stage, allowed the astronauts to descend from lunar orbit and set down on the moon's surface. This vehicle was a true spacecraft in that it was capable of operating only in the space environment. Having used its descent engine to land on the moon's surface, the lunar module would be required to do what had never been done before: lift off from a planetary body other than Earth. Due to the extremely different physical characteristics of the lunar environment, the dynamics of launching a spacecraft from the moon's surface greatly contrast the dynamics of an Earth launch. The black sky during the daytime bears witness to the fact that the moon possesses no atmosphere to scatter sunlight. Because of the lack of any atmosphere, aerodynamic stress and frictional drag are non-existent
That's going
during
to be
the launch
important
from
when
the
you
moon's
answer some
surface.
questions on the lab.
In
There
contrast
is
to
no
Earth
atmosphere
launches,
on the moon.
streamlining of the spacecraft becomes unnecessary, as the lunar module's protruding components and non-streamlined configuration is of a functional design and presents no problems during launch. In order to provide the thrust required to lift off from the surface and attain lunar orbit, the ascent stage of the lunar module possessed a single rocket engine. Because there was no backup engine and no other means to lift off from the moon's surface, a malfunction could absolutely not be tolerated. The single engine had
Yeah,
to
you
work.
couldn't call AAA.
The
Hey,
engine
hey,
used the
can you
most
help me out?
reliable propellants available: hydrazine and nitrogen tetroxide, 2 compounds which spontaneously ignite upon contact with each other. Because the gravitational acceleration of the surface of the moon is only 1.7 meters per second squared, the 5,000 kilogram ascent stage has a weight of only 8,500 newtons, a weight 6 times smaller than that which it would have had on the surface of the Earth.
Okay.
Because mass remains constant throughout the universe and is not affected by gravity, the spacecraft's 5,000 kilogram mass requires the same definite amount of net force to achieve a given.
Okay. Now, well, I want you to listen to what was just said, and we're going to summarize this. So these are the same numbers that you're going to have in your lab. So when you're on the moon, gravitational acceleration on the moon is negative 1.67 meters per second squared. It's negative 9.8 here. You have a 5,000 kilogram mass ship. That's the same number that you're going to have in your lab. So if you're on the Earth, that 5,000 kilograms, if you multiply that by negative 9.8 meters per second squared, you get about negative 50,000 newtons. So on the Earth, that ship would weigh about 50,000 newtons. If you go to the moon, where G is like negative 1.67, that's about 8,300 newtons of force. So the gravity mafia on the moon is much weaker than it is on the Earth. So, but what's important is what stays the same is the mass. So you have a 5,000 kilogram mass here, you have a 5,000 kilogram mass on the moon. That stays the same. It weighs about 50,000 newtons on the Earth. So on the Earth, if you're going to get that thing up in the air, you'd have to generate over 50,000 newtons of force to get it to go up in the air. On the moon, because it only weighs about 8,300 newtons, you only have to generate about 8,300 newtons of force to get it up in the air. So that's why it's easier to take off from the moon than it is from the Earth, because you don't have to pay off the gravity mafia near as much. Okay, so let me hand out the lab. There's 2 pages to this, and I'll explain what those are. Here we go. Okay. So what's going to happen tomorrow is that up here at the front of this, I've given you the parameters of the mission. G is negative 1.67, the mass is 5,000 kilograms, and this is going to be important. Anything going down and left is negative, whether that's displacement, acceleration, force. Anything going up and right is positive. So, tomorrow, what's going to happen is that why can't I... This is weird. So tomorrow, you guys won't, but your other compatriots will. You're going to run a program called Interactive Physics 2000. These are on the laptops. So what's going to happen is that why is it not? Oh, there's supposed to be H drive on there, but it's not there for some reason. Okay. So tomorrow, what your compatriots are going to do, are they're going to try and land this ship. So I'm going to just do this right quick so you can see what's going to happen. So what this button does is that this controls the value coming out of this main thruster. So you're always going to have a downward force of about 8,300 newtons. So this thruster here, if you want to have a positive net force and a positive acceleration, that value has to be above the weight of the ship. If the value from here is less than the weight of the ship, you're going to have a negative acceleration. Now, negative acceleration doesn't necessarily mean that you're going down. It just means that you have a negative acceleration. You could have, this ship could be going up with a positive velocity and a negative, so you could have a positive velocity and a negative acceleration, and it could be slowing down. You could have a negative velocity with negative acceleration, and you would be speeding up. So just because you have negative acceleration doesn't mean that you're going down. Now, if you have negative velocity, you are going down. If you have positive velocity, you're going up, okay? That's true, but to get out of this idea that negative acceleration means that you're going down, it just means that you have negative acceleration. So, what they're going to keep track of is the vertical acceleration. This is this AY value. Your vertical velocity. If you're going to land, you have to land with a velocity less than negative 1 meter per second. If you're going faster than that, the system says, oh, you crashed and burned, sorry, you're stuck. This is your horizontal acceleration, and this is your vertical velocity. Now, here's the deal. Vertically, and listen to me, you always, no matter what, the gravity mafia is always pulling down. The moon is a vacuum, okay? So what that means is that horizontally, there are no external forces acting horizontally. So if you give this thing a little bit of a velocity in the horizontal direction, it will maintain that horizontal velocity because there's nothing to oppose it. So it's just like me taking this cart with the wheel sides down, and I give it a little bit of a push. Well, if I give it a little bit of push, it's going to keep going because there's nothing to slow it down. Now, if I let go of it vertically, it's always going to accelerate because I have a vertical external force. But on the moon, I don't have any horizontal external forces. So keep that in mind when you answer some of these questions. So let me run it right quick. And beautiful. Okay. This is what I do after school. All right. No, not really. Okay, so keep in mind what this is showing. This is keeping track of your vertical velocity. This is a velocity time graph. What does the slope of a velocity time graph give you? Acceleration. So notice that this slope is changing a lot. So think this through. Force net equals what? Mass times acceleration, right? So if I'm going to change the acceleration, what do I have to change? What'd you say? No, I can't change the mass. What was I controlling? The force, right? So if I change my applied force, I change my net force. If I change my net force, guess what? I change the acceleration, I change the slope of the velocity time graph. Okay? Keep that in mind. All right, so here's what you need to have done. So here's how this deal is going to play out. Typically, you all would be back in here tomorrow and you would actually run the simulation. You're going to have to trust the others at home that are going to be in here to do that. So what I want done tomorrow is I want the front page, front and back done. So up here I've given you all these parameters. What's going to happen on tomorrow is that your compatriot's going to run the lab, and then we're going to get the numbers to actually fill in the second page. And then everything is going to be due on Monday. Okay? So what you want to have done, if you want to zoom in, okay, tomorrow, if there's ever time that you zoom in, either tomorrow, at first block, or during third block, the people that are here, I'm actually going to look over this assignment, and I'm going to tell them if their answers are right or wrong. Because like NASA isn't going to turn you loose on a rocket if you can't do simple Newtonian physics. So what's going to happen tomorrow, there are people that are here, and listen to me, you people that are watching this at home, you have this front page done. Because I'm not going to give you a laptop and this program until all of this is done and done right. So if you want to, okay, even tonight if you get this front page done, if you want to send me that, I'll look over it and I'll tell you, oh, this is what you need to correct. You don't have to, okay? But if you want to, I'll look over this and I'll tell you anything that you need to change. So, Some of these you're gonna have to make some free body diagrams, there's velocity time graph, there's a whole bunch of things that are gonna play into this. So, that's the drill. So, have the front page done. Tomorrow, once they actually do this, I'll record that so you can see what's happening with laptops. I'll send you the data that you need, and then everything is gonna be due on Monday. Okay? Clear as mud? Got it? Great? Okay. So, we're done. That was a long one.